Hi, this is Lakshmanachari, working as Assistant Professor in Department of Cyber Security, Institute of Aeronautical Engineering, Hyderabad. So, in this lecture, we are going to discuss about the input-output instructions and interrupter. So, computer. So, computer is an electronic device that can be programmed to accept the data, process it, and generate the results. So, using the computer, we are performing several operations. So, a computer can serve no useful purpose unless it communicates with the external world. So, to the computer, we are connecting many input devices and output devices. Okay. So, the instructions and data stored in memory must come from some input device. So, we are connecting some input devices with the computer in order to accept the data to the computer. So, after accepting the data from the input devices, then the computer will process the input data and it generates the results. So, after generating results, that results can be given to the user using some output devices. Okay. So, we are connecting the input devices and output devices with the computer. So, without connecting any input devices and output devices, the computer cannot serve any useful purpose. Okay. So, the commercial computers include many types of input-output devices. To demonstrate the most basic requirements for input and output communication, we will use an illustration terminal unit with a keyboard and a printer. So the terminal unit you can see here. So here we are using one input device and one output device. So we are using keyboard as the input device and printer as a output device. And in here we are using two registers. One is the input register and another one is a output register. So these two registers are 8-bit. So 8-bit registers. So 8-bit registers. So see, so we are using here transmitter interface. So this transmitter interface and receiver interface are the serial communication interfaces. Serial communication. So the keyboard. So keyboard is an input device. Whenever we stuck a key on the keyboard, it will generate a 8-bit alphanumeric code. So that code will transmit through the transmitter interface and it will be loaded into the input register. Input register. So after that, from the input register, it will be accepted by the accumulator of the computer, and again from the accumulator it will be loaded into the output register. Okay, so from the output register it will be the data will be given to the printer in order to print through the receiver interface. So this is how the communication will takes place from the input device to the output devices. The input-output terminals send and receive information. So we have seen input and output terminals. So that input and output terminals can send and receive the information. The amount of information transferred will always have 8 bits of an alphanumeric code. So whenever we press any key on the keyboard, then it will generate a 8-bit alphanumeric code. Okay. So the information generated through the keyboard is shifted to an input register. So whenever the input, whenever the 8-bit alphanumeric code is generated, then that will be given to the input register through the transmitter interface. And the information for the printer is stored in the output register. So see here, whatever the information we wish to pass to the printer, so that will be stored in the output register. So from the output register, the data we are giving to the printer to give the printer. So registers input register and output register communicate with the communication interface serially and with the AC in parallel. So if you look into the these two 8-bit registers, input register and output register. So these two, the input register, it performs two operations simultaneously. That is one of the operation is it can communicate with the transmitter interface and it also communicate with the accumulator simultaneously. So that means both operations it is performing parallelly. So similarly, the output register. So the output register also it is communicating with the receiver interface simultaneously. It is also communicating with the accumulator. So the input register and the output register it is performing two operations simultaneously. The transmitter interface receives information from the keyboard and transmits it into input register. The receiver interface receives information from the output register and sends it to the printer serially. And the 1-bit input flag is a control flip-flop. So here we are using two flags. One is the input flag and the other one is a output flag. So these two are one bit flags. That means either we can store logic 0 or logic 1. So the default value of the input flag is logic 0 and the default value of the output flag is 1. Okay. So see the process of information transfer is as follows. So that means when the input data is generated using the keyboard, how the data will be transmitted to the output device. So in between we are following some sequence of operations. So let's see one by one. So initially the input flag FGI. So the input flag is the shortly we can call FGI, input flag. So that is cleared to 0. So that means the default value of FGI is equal to 0. So it indicates that the FGI is equal to 0. It indicates that the input register it doesn't have any data. So that means the input register is empty. Next, the second point is when a key is stuck on the keyboard, then it will generate a 8-bit alphanumeric code. And that generated 8-bit alphanumeric code will be shifted to the input register. And whenever the 8-bit alphanumeric code is loaded into the input register, something data, 8-bit data. Okay, whenever that 8-bit alphanumeric code is loaded into the input register, then the input flag. So input flag value will become 1. So that means the 1 indicates that the input register it contains some information. Okay. So as long as the flag is set, so as long as the FGI is equal to 1, the information in INPR cannot be changed by striking another key. So until the data which is available in the input register is accepted by the accumulator of the computer, no another 8-bit alphanumeric code is accepted by the INPR, input register. So the input register can accept one more 8-bit alphanumeric code only if the already existed data in the INPR is accepted by the accumulator. Okay. So next point, the computer it checks the flag bit. If it is 1, the information from INPR is transferred in parallel into the accumulator and FJ is clear to 1. So whenever the data, see here, so this is a INPR. Whenever this the 8-bit alphanumeric code is generated, that will be loaded into this input register. So from the whenever the accumulator of the computer is accepted the data, then the FGI will become 0, because whenever the input register is loaded with some information, then FGI will become 1. After the input register data is accepted by the accumulator, then the FGI value will become 0. So FGI is equal to 0. It indicates that the input register it doesn't contain any information. So that whenever if you press any key on the keyboard, then again the 8-bit alphanumeric code will be generated and that will be shifted to the input register. Once the flag is cleared, no information can be shifted into INPR by striking another key. Okay, so whenever this FGI is equal to 0, then only the input register can accept one more 8-bit alphanumeric code by pressing another key in the keyboard. So that is about how the data from the input device will be passed to the input register. Similarly, whenever the accumulator is accepted that input register data, then that can be given to the output device. So output device is a printer. So after accepting the data from the input register by the accumulator, it will be given to the output register. It will be given to the output register. So the default value of the FGO is equal to 1. The default value of the FGO is equal to 1. So FGO is equal to 1. It indicates that the output register is empty. Whenever the output register is loaded with some information, then the FGO will become 0. Whenever if the output register contains any information, then the FGO will become 0. Then from that output register, that 8-bit alphanumeric code will be given to the printer through the receiver interface. Then using the printer, it will print the code. Okay, so this is how the input from the keyboard will be transmitted to the output device printer. So coming to the input-output reference instructions. So already we have seen the instructions are classified into different types. Mainly 3 types we have classified, that are input-output reference instructions, and second one is memory reference instructions, and the third one is register reference instruction. So these are the 3 main important classification of instructions. So already in previous class we have seen about the register reference instructions and memory reference instructions. So now we are going to have a look on input-output reference instructions. So these input and output reference instructions are needed for transferring information to and from AC register, that means accumulator. So using this input and output instructions, we can read the data from the accumulator or we can send the data to the accumulator. So mainly it is useful for transferring information. And the second purpose is checking the flag bits. So we have 2 types of flags, that are FGI and FGO, input flag and output flag. In order to check these flags, we are using this input-output instructions. And the third one, controlling the interrupt facility. Whether we want whether the system wants to allow the interrupts or not. So for controlling the interrupt facility, we are using all these input-output reference instructions. So for these 3 purposes, we are using input and output reference instructions. Okay, so how we can determine the input and output instructions. So for that, it is based on the opcode bits of the instruction. So if you look into the instruction, so it contains 16 bits, 0 to 15. Okay. So 0 to 11, it represents the input or output operation or address. It represents the address of the operator. And from 12, 13, 14 bits of the opcode are 1. So 12, 13, 14 bits of the instruction register are set to 1. Then it will be register or IO reference instruction. So it may be a register or IO reference instruction. So if the 15th bit, so based on this 15th bit, we can decide whether that is a register reference instruction or IO reference instruction. So if the 15th bit, so that is I. So I is a indirect bit. So if I is equal to 1, then that is a IO reference instruction. IO reference instruction. So if I is equal to 0, then that is a register reference instruction. So in this way, we will decide whether the given instruction is related to the IO reference instruction or register reference instruction. So for input or output reference instruction, the 15th bit, 14th bit, 13th and 12th bit of the instruction register should be logic 1. Okay. So that's why the operational code will be 4 ones. So this is 15th bit, 14, 13, 12. So when all the bits of this 15 to 12 is set to logic 1, then that can be considered as a input output reference instruction. And also, so that means D7. So D7 is equal to 1 and I is equal to 1. So this is called D7 and this is called I. So that D7 and I should be equal to logic 1. Then that type of instructions are considered as input output reference instructions. So these instructions are executed with the clock transition associated with the timing signal T3. Each control function needs a Boolean relation D7 I T3, which we designate for convenience by the symbol P. So this D7 I T3, it was designated by the letter P. Okay. So when the D7 I T3 is equal to 1, then this input output reference instructions will be executed. So see here, you can see. So suppose if you consider a input or output reference instructions. So see here. So during T0, the program counter address will be loaded into address register. During T1, the instruction will be placed in instruction register, and during T2, the instruction will be decoded, and during T3, the instruction will be executed. Okay, so T0, T1, T2, T3. So during T3, the IO instruction will be executed. So see here. So D7. So based on the D7, we will decide whether that instruction is a memory reference instruction or register or IO reference instruction. So if D7 is equal to 1, that may be a register or IO reference instruction. If D7 is equal to 0, then that is considered as a memory reference instruction. After deciding the type of the instruction, then come to the I. So if I is equal to 1, then that is a IO reference instruction. If I is equal to 0, that is a register reference instruction. So during this T3, the IO reference instruction will be executed. Okay, so this is about the flowchart for the instruction cycle. So how the instruction will be fetched, decode and executed. So this is a fetching phase. So it is a fetch. So every instruction, it has to undergo these three phases: fetch phase, decode and execute. So then only the next instruction will be fetched from the memory. So this is a decode and this is a execute. Okay. So see here. So here we have given some input output instructions. Okay. So that are, so initially the sequence counter will be set to 0. So we are clearing the sequence counter. So first instruction is a INP. INP. So that means input character. Input character. So what is input character? So whatever whenever a key is struck on the keyboard, so 8-bit alphanumeric code will be generated, and that generated data will be placed on the input register. Okay. So from the input register, that we are giving to the accumulator. So but here the accumulator size is a 16-bit data, but the input register is a 8-bit register. So that's why the 8 bits of the input register we are sending to the accumulator lower byte. So lower byte means accumulator 0 bit to 7th bit. So total 8 bits. So we are copying the input register data into the lower byte of the accumulator. So that is called INP. Input character. Next, output character. So this output character, it will execute during PB10. So input character, it will execute during PB11. Okay. So output character. So after accepting the accumulator, from the accumulator, we are sending the data to the output register. So this one. So see here. So for the input register, so whenever the input register data will be transferred to the accumulator, what will happen? So when the input register contains data, the FGI will be 1. Whenever that input register data will be shifted to the accumulator, then the input flag will become 0. Similarly, output character. So whenever the accumulator data is accepted by the output register, so before accepting the data to the output register, so FGO will be 1. But after loading the content from the accumulator to the output register, its value will become 0. So that's why 0 will be loaded into FGO and 0 will be loaded into the FGI. And third one, SKI. So skip on input flag. Skip on input flag. So if so this SKI will execute during PB9. And if FGI is equal to 1, so if the input flag is equal to 1, then we have to skip the instruction. So how we can skip the instruction? By incrementing the program counter. So PC plus 1. So that is nothing but incrementing the program counter. So after incrementing the value, again that incremented value will be loaded into the program counter itself. And next to SKO. Skip on output flag. So this SKO will execute during PB8. And it will be execute when FGO is equal to 1. If FGO is equal to 1, then it will skip the instruction. So by incrementing the program counter. Next one, ION. So interrupt enable on. So this will execute during PB7 timing signal. So IEN is one we are loading into the IEN. So by sending one to the IEN interrupt enable, then the interrupts will be enabled. If you want to disable, then we can load the 0 into the IEN bit. Okay, so last one is a IOF, interrupt enable off. So if you want to disable the interrupts from the external devices, then we can load the 0 value into the IEN register. So that the interrupts will be disabled. So these are the input output instructions. And coming to the interrupter, program interrupter. So interrupter. So interrupt is a signal from the external devices. Interrupt means which will breaks the continuity of the program. Continuity. Okay. So the process of communication is just described is referred as the programmed control transfer. The computer, it keeps checking the flag bit, and when it finds it set, it initiates an information transfer. So this type of data transfer is called programmed control transfer. So that means here the CPU has to continuously monitor the flag bits. If the flag bit is set to logic 1, then the data transfer takes place. So otherwise there is no data transfer takes place. Okay, so here what will happen? So the CPU will spend more time on checking this flag bits. So that means some considerable amount of CPU's time is wasting here. So that is a drawback with this programmed control transfer. So the difference of the information flow rate between the computer and the IO device makes this type of transfer inefficient. Okay, so this type of transfer is inefficient because the speeds of the data transfer rates of the computer and IO devices are different. So the computer can process the instructions at a faster rate because the computer can execute million instructions per second. So that means the speed of the computer is high when you compare with the IO devices. So IO devices can transfer the data at a slower rate. Okay, so that's why their data transfer rates are different. Okay, so in that case, this method it becomes inefficient. Okay, so to see why this is inefficient, consider a computer that can go through an instruction cycle of 1 microsecond. So the instruction cycle time is 1 microsecond. So assume that the input and output device can transfer information at a maximum rate of 10 characters per second. So here we are assuming a IO device that can transfer 10 characters per second. So that means in order to transmit a 1 character, it requires 1 lakh microsecond. So that is equal to 0.1 second. So that is equal to 0.1 second. So that means here, see, the computer will check the flag bits 50,000 times between each transfer. So because here we are transmitting byte by byte. Okay, first we will transmit 1 byte. After that we are checking the flag bit. Okay, after checking flag bit, again another byte. So like that we are transmitting the data byte by byte and by checking the flag bits. So here the CPU is spending more time on checking this flag bits. So that's why this method becomes inefficient. So for the better method, we are going for the another method. Okay, so that is called interrupt initiated data transfer method. So see here. So we are going for the alternative method. So what is the alternative to the programmed controlled procedure is to let the external device inform the computer when it is ready for transfer. So previously in the first method, programmed controlled procedure, the CPU has to check continuously the flag bits. But here, no need to check the flag bits. Whenever the CPU is whenever the IO device is ready to transfer the data, then the interface unit will generate an interrupt to the CPU. Then the CPU will involve in the data transfer. Okay, so that is a benefit with this interrupt initiated data transfer. So this is achieved with the interrupt facility. While the computer is running a program, it doesn't check the flags. It doesn't check the flags. However, when a flag is set, the computer is momentarily interrupted from proceeding with the current program and is informed of the fact that a flag has been set. A computer deviates momentarily from what it is doing to take care of the input or output transfer. It then returns to the current program to continue what it was doing before the interrupt. So whenever the interrupt is occurred, then the CPU will stops the currently running program and it will go to the corresponding interrupt related program. Then it will execute all the statements in that interrupt related program. Then it will return back to the next instruction of the currently running program. Okay. So in this way, it will service the interrupts. So basically, the data transfer between the CPU and IO device will takes in three ways. First one is a programmed IO data transfer. Second one, interrupt initiated IO data transfer. Third one, direct memory access data transfer. So these are the three main data transfer methods between the CPU and the IO device. So first one, programmed IO data transfer. So already we have seen that. So this programmed IO data transfer will take place result of an IO instruction. So by executing some IO instructions, then the data transfer will take place. Need CPU's continuous monitoring. So in this method, the CPU's continuous monitoring is required because the CPU continuously it has to check input flag and output flag. So that's why here. So that means here unnecessary usage of CPU. So the CPU is utilizing its time for checking the flag bits, but it is not the it is not the purpose of the CPU. So CPU it has to execute some important instructions and programs. But instead of executing some important programs, it is spending time on checking the flag bits. Okay, so that's why this is a drawback with this programmed IO data transfer. So in order to overcome the drawback, we are going for the interrupt initiated IO data transfer. So in this, the data transfer will occur upon occurrence of an interrupt signal. So we have a CPU, we have a IO device, and in between we have a interface. So when the IO device is ready to transfer the data, then this interface unit will send a interrupt, interrupt to the CPU, so that the CPU can understand that the data transfer should require, so that the CPU will involve in the data transfer. Okay, so in this way, so this reduces the unnecessary usage of the CPU's time. So the CPU will involve only if the data transfer takes place. Okay, now when the data transfer is not taking place, then the CPU will not involve. Third one, direct memory access. So direct memory access. So no unnecessary usage of the CPU. So in direct memory access, so we are transferring the data from IO device to the memory without involvement of the CPU, because the CPU it cannot handle the large amount of transfer. So that's why we are directly transferring the data from IO device to the memory without involvement of the CPU. And IO processor monitors the data transfer. So we have a IO processor. So that IO processor will monitors the input-output data transfer and interface handling capability under DMA. Okay, so this is a data transfer in a CPU program IO operation. Program IO operation. So we have a IO device, and we have a device CPU, and we have a interface circuit. So whenever this IO device is ready to transfer the data, it places a data in the IO bus. After that, see, after that, this will send the IO device will send a data valid signal to the interface. So the data valid it informs that the valid data is placed in the IO bus. So after that, the data which is available in the IO bus will be placed in the data register. Will be placed in the data register. Then that data register will be accepted by the CPU using the data bus. Okay, and the CPU the CPU can access the IO device. The CPU can access the IO device because so many IO devices we are connecting with the CPU. So different IO devices. So every IO device it is having some unique address. Unique address. So using that address only, the CPU can access the IO devices. So that's why that address information will be sent through this address bus. And this is a status register, and one flag is there, F. Okay. So whenever initially this flag will be 0. Initially the flag will be 0. So whenever the data is loaded with the data register, then this flag becomes 1. The flag becomes 1. So flag is equal to 1. It indicates that the data register is having some valid data. So that the interface unit will send a data accepted signal to the IO device. Okay. So this CPU. So when the CPU, when this flag is equal to 1, when f is equal to 1, the CPU can accept or can read the data which is available in the data register. So that is called IO read, IO write. Okay. So this is a program IO operations. And this is a flowchart for CPU program to input data. So CPU first it will read the status register. It will read the status register. After that, it checks the flag bit. It checks the flag bit. So if flag is equal to 1, if flag is equal to 1, so it indicates that the data register having some data, so that the CPU can read the data register. Suppose if the flag is equal to 0, flag is equal to 0 means the data register it doesn't contain any data, so that it continuously checking the status register. It continuously checking the status register. Okay. So if the data register contains data, then that will be transferred to the memory. And we are checking the condition, is the operation completed or not. If the operation complete, then it will continue with the remaining program. Suppose if the operation is not completed, again it has to read the status register. So this is a flowchart for the CPU program. And coming to the flowchart for interrupt cycle. So already we have seen what is interrupt. Okay. So whenever the interrupt is occurred, then the CPU will stops the currently executing program and it will enter into the interrupt related program. Then it will execute the interrupt related program and it will return back to the next address of the currently running program. So see here. So this is R. So what is R here? R is the interrupt flip-flop. So this R interrupt flip-flop. So here we are checking this interrupt flip-flop. So R is equal to 0 and R is equal to 1. So if interrupt is occurred, that means if R is equal to 1, then we have to execute the interrupt cycle. Suppose if R is equal to 0, that means interrupt not occurred. If interrupt not occurred, we have to execute the instruction cycle. So here R is equal to 0. So so interrupt not generated. So that means instruction cycle has to be executed. So what is instruction cycle? Instruction cycle, it has different phases. So first one is a fetch phase, fetching, decoding. So instruction first it will fetch from the memory and after that it will be decoded. Then it will be executed. Okay, so that is a instruction cycle. Suppose during execution, if any interrupt occurred, so IEN, so interrupt enable. So IEN is equal to 0. So that means interrupts will be disabled. So that's why then it will checks the R. So IEN is equal to 0. IEN is equal to 0 means interrupts are disabled. So no interrupts will occur. Suppose if IEN is equal to 1. So that means interrupts are enabled. So if interrupts are enabled, then we have to check the two flags, FGI and FGO. First we are checking the FGI. If FGI is equal to 1, so what is FGI? Input flag. So if interrupt is occurred, then we have to execute the interrupt cycle. So that's why we are loading R. One is loading into the R. So if R is equal to 1, then it will be a interrupt cycle. Okay. Suppose if the FGI is equal to 0, then we are checking the output flag. Similarly, if the FGO is equal to 0, then we are checking a R again. Suppose if FGO is equal to 1, in that case also we have to load 1 into the interrupt flip-flop. So see here in interrupt cycle. So interrupt cycle, what will happen in interrupt cycle? So this is a main program. So main program. So when in the main program somewhere the interrupt is occurred. So when interrupt is occurred, the program control is transferred to the corresponding IO related program. Then all the statements in that IO program gets executed. Then it will return back to the next instruction of the program, and it will continue the executing its remaining instructions in the main program. Okay. So store a return address. So that means here the program control is transferring from IO interrupt program to the main program. In order to come back to the main program, so we have to store the return address. Return address is nothing but the next address of the next instruction in the main program. So that we have to load into the location 0. So that means a PC of M of 0. Next, branch to one location. So we have to branch to the first location. So that's why one will be loaded into the program counter. Okay. Then IEN is equal to 0. So because here interrupt is serviced, interrupt executed here. So that's why no more interrupts. So IEN will be loaded with 0. And similarly R is equal to 0. If R is equal to 0, then instruction cycle will be executed. Okay, so this is a interrupt cycle. So that you can we can demonstration of the interrupt cycle. So this is a before interrupt occurred. This is after interrupt cycle occurred. So before interrupt takes place, see here we have a memory, and this is a memory location address 0, and this is a memory location 1. So in the memory location 1, we have a 0 BUN instruction. BUN means branch unconditionally. So that means without checking any condition, the program control will be transferred to this address. So 1120. So 1120. So what is this 1120? In the 1120 location, we have a IO related program, input or output related program. So it will execute. And the last instruction is a 1 BUN 0. 1 BUN. So this one indicates that it is a indirect address, and this is the address of the operand. Okay. So you can see after interrupt cycle occurred. So see here. So this is a memory location 0, and this is a memory location 1. Okay. So here the main program. So here at 255 location the interrupt is occurred. In the main program at the address 255 the interrupt occurred. So what will happen when interrupt occurred? What will happen? It will go to the IO program. It will go to the corresponding IO program. So here in this, what is the 0? Okay, here the interrupt is occurred. So what is the next address? Next address is this one, 256. So this is the return address. So this 256 we are storing in memory location 0. Okay, so 0 BUN 1120. So that means whenever the interrupt is occurred, then the program control will be transferred to the 1120 location. So in 1120 we have a IO program. In IO program, what is the last instruction? 1 BUN 0. So 1, what is 1? This one specifies indirect address. So that means this 0 is not the address of the operand. Okay. So it is a address of the memory location that contains operand. Okay. So 1. So 1 means indirect. So it will go to the 0 location. So in 0 location, we have a return address. So using this return address, so the program control will be transferred from this IO program to the main program. Okay. So this is a interrupt cycle. Okay. So in this video, we have seen different input and output instructions, and also we have seen about the interrupt and its interrupt cycle. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.